Right, so the question on everybody's lips is, why does the resistance of a metal wire increase as temperature increases, which we know is to do with the fact that the vibrations in the metal ions that are in the metal lattice structure for the chemists to get excited about, those vibrations make it more difficult for electrons to pass through without colliding with the metal ions. So as temperature increases in a metal wire, resistance also increases. Okay, but why with the thermistor did the resistance decrease as the temperature increased? We need to understand a little bit about semiconductors. Now, the most famous semiconductor we have is silicon chips, not what you have for dinner, what are in your computer and your mobile phone. That's the most famous and useful semiconductor. We've also got gallium, which is another, or geranium, or something like that. Geranium or something. Anyway, so another semiconductor that we can use, and that's graphene as well as a semiconductor. Chemistry rubbish. So we want to know, why is it that as temperature increases in a semiconductor, why does resistance decrease? So one thing to note, we're talking about semiconductors here, so the number of free charge carriers is in between a conductor, where n is to the power of 28, 18 orders of magnitude greater than a semiconductor, and an insulator will have very few, if any, free charge carriers, so close to zero. But semiconductor is somewhere there in the middle. Silicon has it's about 9.8 times 10 to the 9, which is about 1 times 10 to the 10 free charge carriers per cubic meter. So we're there in no man's land in between conductors and insulators. So in order to understand this, what we need to think about is the fact that the silicon atoms, which I'll put here in red, are bound together in a lattice. Okay, now there's not a lot of electrons free in this lattice. We only get the occasional one or two popping free. Okay, so there's one of them. There's a free charge carrier that's popped free from the silicon lattice. There's not many of them, so there being fewer free charge carriers means that it's harder for current to flow. Now, if we increase the temperature, in this semiconductor lattice, what starts to happen is that vibrations in the silicon lattice free up. So let's have them starting to vibrate more as temperature increases. Free up more free charge carriers. So here we have a charge carrier that has been freed up because it has been shaken loose from the silicon atom here by vibrations caused by increase in temperature. Now, what that means is, if current is flowing to my right, that means my free charge carriers are going to move to the left. Okay? Yeah? And there being more free charge carriers means that the resistance has decreased. But what has happened here, when this free charge carrier has been freed up by vibrations in the lattice, what has got left behind here will have had a positive silicon ion left behind. Okay? Now, what can happen from a neighbouring silicon atom, what can happen is an electron can jump. It's not a free charge carrier because it's bound to the atoms, okay? But a electron can jump from this atom to this one, and so what we have left here is positive charge. So the positive charge, which I'm going to call it a positive hole, okay? This positive charge that's on that ion, electron jumps from the neighbouring one that way, so the electron's physically moving that way, but these are not free charge carriers, they're bound to the atoms. So what, in reality, what I observe is that a positive ion, the positive charge moves from that ion to that ion. So I get this positive charge, or this positive hole, moving in the opposite direction. So the positive hole moves that way. So in effect, as temperature increases in my silicon atom, I get free charge carriers shaken free from the atoms here. So N, my number of free charge carriers, increases, but also I get this positive charged ion, or this positive hole in the lattice, moving in the opposite direction. So not only do I get more free charge carriers, but I also get these positive holes moving in the opposite direction. So this positive hole is carrying charge that way, and the electron that's being freed up is carrying charge that way. And this is why the relationship is not linear, because for every electron I get freed up, so for every electron that increases my number of free charge carriers, I also get a positive hole taking charge in the opposite direction. So as temperature increases and the number of free charge carriers increases, the resistance decreases quite drastically. Okay. Now, why do we need to worry about these positive holes and stuff? We need to think about these positive holes because in a moment we're going to talk about doping semiconductors. That's adding a contaminant, a different element to the semiconductor lattice, and that different element is going to have a drastic effect on the resistance of the semiconductor, or the number of free charge carriers in the semiconductor, or the number of positive holes. Okay, so in your semiconductor, remember that you get free charge carriers, electrons freed up, and you also get positive holes carrying the current, the charge in the opposite direction. Okay, so in this case a hole is positive, not negative.